Hello, my name is Jose Garcia-Cejas,
I'm Harrison Mesh.
And I'm Logan Mesh.
and we will be tackling Problem B, an AI Ouroboros. So, as an introduction, the amount of AI generated content on the internet is growing at a rapid pace and has been over the past couple years. This will lead to a larger amount of synthetic training data in future model training data, which could possibly affect the quality of the AI. We want to see exactly how this quality will be affected. The term model collapse refers to the degradation of model quality over a series of models, where the output of one becomes the training data for the next. This is important to study because our reliance on AI has been increasing over time, and a model collapse could cause millions of dollars in damage. The previous literature has studied two main scenarios: replacement and accumulation. Replacement is where new data created by AI completely replaces all older training data, and this causes model collapse to occur very quickly. Accumulation is where new output created by AI is added onto the previous training data, which is found to completely prevent model collapse. We find both of these to be unrealistic. One, because the internet stores data over time, so replacement is unlikely. And accumulation is also unlikely because data gets corrupted over time. So we will be studying the three scenarios: replacement, accumulation, and a mix of the two. For our assumptions, we've made 8 in total. The first one is interactions between AI generated and human generated data can be modeled via a Lotka-Volterra model. 2 and 3 is, as of 2025, 30% of potential training data on the internet is synthetic, and 80% of people with internet access actively publish content online. AI models are trained on new data based on the accumulation model, replacement model, or some mixture of the two. AI quality is a factor in how fast AI generated content spreads. Our sixth one is ChatGPT usage data is accurate and correlated with the spread of AI generated data. The quality of data for a certain AI is influenced by synthetic data generated by all AI models. And different AI companies may use different methods of introducing and handling synthetic data.
We decided to base our model off of the Lotka-Volterra model, which is usually used to study interactions between predators and prey. We believe that the interaction between AI content and human content can also be modeled this way, as they both rely on each other for if they grow or if they shrink. However, we made some changes to further fit the problem. We used the sigmoid function to restrict the range of humans per capita to be between 0 and 1, as we do not expect a large amount of humans to enter the internet. We also added a new factor called quality to indicate that AI usage will grow more rapidly if it is more powerful. We decided to range this between 0 and 1, with a new parameter epsilon to determine its growth rate, and a parameter zeta determines how training data corruption works. Our parameters for alpha, beta, gamma, and delta are the same as in the Lotka-Volterra model. We note that t is actually in years for this model, and that both the humans and robots have their values measured per capita, although the robots can be larger than 1 because it's possible for there to be more robots than there are humans on the entire internet. Our initial parameters were mostly based off our assumptions, although we did make some educated guesses to make the model behave well. Additionally, note that we set the initial quality to be 0.5, indicating that AI has the most to gain the quickest in the current time span.
So we're going to talk about fixed points now, which are important because they describe how the model might behave in the long term. So the first two are under extreme values of functions. So if there's no AI content and no human content and the quality is 0 or 1, those are fixed points under the equations. The third fixed point is a Lotka-Volterra-like solution where the quality is 1, the equations simplify down to a version of a Lotka-Volterra equations where the human per capita amount is capped at 1. And so we get very similar solutions, except that the R term has this factor of 1 minus h. And what's important to know is that the model does act relatively stable near these points and approach this. You'll see that in scenarios where the quality approach is 1, the human and robot populations tend to approach these fixed points. There's also a fourth fixed point, which I like to call the model collapse fixed points. This is because this is a fixed point where the quality is less than 1, and will only occur when the data is greater than 1, and in particular where if you solve for q equals k using that bottom equation, so zeta is larger than 1 plus gamma times beta divided by alpha times the quantity delta minus gamma, then the quality will be less than 1. And there's also this fixed point that the model is relatively unstable towards. As you'll see in our later scenarios, it will tend to oscillate around it, sometimes even reaching back to qualities of 1 and then going way down, and so on. Now we're going to discuss some of the scenarios about our model. We simulated using Euler's method because there's no analytic solution to the lockable Terra equations or to our adjustment to those equations. In scenario 1, the accumulation hypothesis, we see that the quality of robots always increases and quickly reaches 1, and robots generally dominate the internet. In scenario 2, we see the quality varies greatly, and the robots never truly take over as the quality worsens whenever the amount of robot content spikes. This is this kind of like oscillatory behavior near this fixed point that does exist. In scenario 3, if we use the mixture of accumulation and replacement, we see that under our values, the models do initially collapse within the first, say, 10 years, like in scenario 2, but they do rebound to perfect quality and a robot-dominated internet, just like in scenario 1.
To extend our model to include multiple AI companies, we decided to introduce more variables for different kinds of robots and their qualities. The rate of change for humans and quality depends on the overall robot population, whereas the rate of change of each robot depends only on their own population. We also use a matrix of zeta values to indicate relations between different types of AIs.
Now we have a couple more scenarios with this multi-AI model. We see that with competing models that have relatively low zeta values, we see that both models do reach good quality, but the model with better training data reaches a state faster and becomes much more dominant in terms of the market share. We see that in scenario 5, where one model is relatively bad and uses the replacement hypothesis, that only one model ends up surviving, and the other one crashes down. And in scenario 6, we see something similar to scenario 2 with multiple AI collapse, where both of them crash in terms of quality, and still one dominates. In scenario 7, this is a significant one, that if both AI models do poorly with their own data, but do better with each other's data, that they will both survive, unlike in scenario 2, and they will both exist in relatively large proportions. And in scenario 8, if we assume the reverse, where both models do worse on each other's data, the model with the higher market share will eventually take over fully, like we saw in earlier scenarios.
For sensitivity analysis, we looked at scenario 3, which we believe is the most likely to happen in practice with one AI model. And we changed the values of the initial parameters and the variables by 10% or 50%. We noticed that for small changes, there was generally very little effect on the overall results. Robots were the most greatly affected. And for 50%, we actually could not do this with humans because that would be outside of the domain, but generally the effects were much larger, although the overall behavior was the same.
We found that model collapse only occurs in the worst case replacement scenarios, and in the rest of the scenarios, model quality may increase or decrease slightly in the short term, but will end up being high in the long term. When multiple models interact, one model is often dominant in the long term, and the existence of multiple AI models can prevent model collapse and lead to healthy competition if models improve when trained on each other's data. We have some limitations. For example, we only examined 8 possibilities with at most 2 competing models and with only select preset parameters. Our model also fails to consider breakthroughs in model training that could change parameters over time. Our model does not consider possible interventions to the training process, such as releasing a new model if the quality worsens, or if there is a cap on the amount of AI-generated data released to the internet. And the biggest one, there is very little clear publicly available data on the amount of AI and human content on the internet that's gathered. And for future studies, we should be able to figure out more data to create better fitting models. Thank you. And here are a list of our references.